Hi, I will be proceeding with Introduction to Spectroscopy. So from here, we will be able to analyze data that we will be gaining from spectroscopy using the Beer-Lambert's law, which is used to interpret data that we will be getting. So let's first take a quick review of the equations that we will be using. So the August Beer law came from two laws which was found by August Beer, which states that the Beer's law, which found the Beer's law. So, from his law, it states that the absorbance of a light in a solution is directly proportional to the concentration of the solution in which light travels. So, from here, from this illustration, we can see that the absorbance, in mathematical terms, we can see that the absorbance is equals to the concentration times the epsilon, which is the molar extinction coefficient or the absorbance capacity of a substance or a sample, wherein absorbance is equal to the log of the incident radiation over transmitted radiation, or absorbance can be equal to the negative log of T, wherein T is equals to the transmitted radiation over the incident radiation. As per this illustration, we can see that the incident radiation would be the radiation emitted from the light source, and the transmitted radiation will be the radiation that was transmitted after it has passed through the medium. So the other law was by Johann Heinrich Lambert, or Lambert's law. From his law, it states that the absorbance of a light in a sample is directly proportional to the distance traveled by light through a medium. So from here, we can say that the absorbance is equals to the epsilon, or the molar extinction coefficient, times the distance traveled by light in a medium, or B. So from this illustration, we can see that B is the length of the distance traveled by light through the medium, wherein this rectangular prism is the medium. So the same thing, absorbance is still equal to log 10 of incident radiation over transmitted radiation, or absorbance is still equal to negative log of T, wherein T is equal to transmitted radiation over incident radiation. So combining these two laws that is used in interpreting data in spectroscopy, we now know that the relationship between concentration, relationship between concentration, absorbance, and the path length of a sample. So we know that the light states that the amount of light absorbed by a solution is an exponential function of concentration and path length of a solution. So we now know that the absorbance is equal to the epsilon times the path length times the concentration. This is by combining the two theories of Beer and Lambert law of, wherein T is equal to the P, wherein P is just equal to the transmitted radiation over the incident radiation. So this from the prior equations that we already have, we know that A can now be expressed into negative log of transmitted over incident radiation is equals to A times the path length times the concentration, wherein the epsilon molar extinction coefficient can be replaced by A, which is absorptivity, which also measures the absorbance capacity of a substance. So by that, we can now derive different equations depending on the given. So we have negative log of T is equals to AB times C, and A absorbance is equals to negative log of T, or absorbance is equal to absorptivity times the path length times the concentration, or absorbance is equals to the molar extinction coefficient times the path length times the concentration. So now let's put it into application. So here we have a problem which says that a solution contains a 4.50 parts per million of a colored species. It is found to have an absorbance of 0.30 at 530 nanometer, centimeter cell. Calculate the absorptivity. So using Beer-Lambert's law, we can get the absorptivity through the formula absorbance is equal to absorptivity times the path length times the concentration. And then through mathematical manipulation, we will be isolating absorptivity, and we will be getting absorptivity is equal to absorbance of the over path length times concentration. Given that we have the absorbance, which is equal to 0.30 at 530 nm, and the path length, which is the size of the cell, which is 2 cm, and the concentration of the colored species, which is 4.50 parts per million. We will just be substituting these values into the derived equation. So we will have 0.30 over 2 cm times 4.50 parts per million. We will have that the absorptivity of the colored species to be 0.33 over per centimeter parts per million. So another problem is a portable photometer with a linear response to a radiation registered a photocurrent of 75.9 microampere with a blank solution in the light path. Replacement of the blank with an absorbing solution yield a response of 23.5 microampere. So here, the first problem wants us to calculate the percent transmission of the sampled solution. So here we know from the simple inspection, we would know that since this is the one with the absorbing solution, hence this is the transmitted radiation, and here, which is just a black solution of the light path, this one would be the incident radiation. So in getting percent transmission, we would just be getting multiplying the formula T, which is equals to transmitted radiation over incident radiation by 100%. So substituting the values for incident and transmitted radiation and then multiplying it by 100%, we will be arriving at the percent T, which is equal to 30.96%. So the absorbance of the sample solution. So from the same problem, commonly absorbance of the sample solution is being found out in the lab. So the absorbance can still but through the application of Beer-Lambert's law, we will be using absorption is equal to negative log of T, wherein T, we will be using here the percent T, and just by dividing it by 100, we will still be getting the same values as this one, which is T. So by taking the negative log of T, which is 30.96 divided by 100, we would know that the absorbance of the sample solution here is equals to 0.509. So also from the problem, it wants us to know the transmittance to be expected for a solution in which the concentration of the absorber is 1/3 of that of the original sample solution. So here, we don't know what is the concentration, but we do know what is the absorbance of the original sample solution. And from the relationship given by the Beer-Lambert's law, we know that it is directly proportional. So if the concentration is multiplied by 1/3, hence the absorbance would also be multiplied by 1/3. So let's put that in mathematical terms. We would be arriving that the absorbance of the original sample solution, which is 0.509, which we have prior computed, will be multiplied by 1/3, which is now 0.170, which is from the expected solution. So using the formula, now that we know what is the absorbance, so from the derived formula that we have before, we know to obtain T, this is the best formula to use. So through mathematical manipulation and by isolating T, we will be arriving at T is equal to the anti-log of the negative value of the absorbance, which is the would be equivalent to the anti-log of the negative 0.170. And by computing that, we would be arriving at the transmittance of the expected for a solution with the 1/3 that of the concentration of the original sample solution would be 0.677. Now here, it wants us to calculate the transmittance to be expected for a solution wherein the concentration is twice that of the original sample solution. So the same concept, however here, it is twice now the concentration. So still, now that we know the relationship between the concentration and the absorbance, we would just be multiplying the absorbance by 0.509 by 2, and we will have now the absorbance of the expected solution, which is twice the concentration, to be 1.018. And using the best formula to obtain T, given that we know the absorbance, we will just be taking the anti-log of the negative value of absorbance that we have computed for the expected solution, which is 1.018. So the transmittance for this one would be 0.096. And for that, I thank you.